Now, the parametric equation, when understood through the diagrammatic representation of a parabola, makes us understand that for a parabola y square equals 4ax, any point on the parabola is taken as at square and 2at is how we understand the parametric equations connected with any point on the parabola. As we had the notations for the circle, similarly we have the notations for the parabola. So if I have a parabola y square equal to 4ax, I usually denote the equation of the parabola in standard form denoted by s, which is y square minus 4ax equals 0, is how we identify the standard notation. That implies if I just have S1, if I would like to find S1, then in this case that is yy1 minus 2a times x plus x1 equal to 0 is how we have the formula for S11. If I want to find S11, then this is y1 square minus 4a times x1, or if I want to find S12, then this is y1 y2 minus 2a into x1 plus x2 is how we understand the various notations where this is referred with the point P x1 y1 with the point x1 y1 on the parabola, but this is referred with 2 points P x1 y1 and Q x2 y2 etc. is how we understand the different notations for the parabola y square equal to 4ax. Now let's try to identify the position of a point in the parabola. Now, as in case of circles, we had three types of positions of a point. One is inside the circle, on the circle, and outside the circle. Now here there are two regions which the parabola divides the plane. Now here if I take, we say that a parabola is said to divide the plane into two regions. This is the parabolic region which goes on all till infinity, but this is the region where the parabola does not cross. So there are two regions which we identify in case of a parabola. Mathematically, we define the regions as the region which contains the focus is called the interior region of the parabola, and the region which does not contain the focus is called the exterior region of the parabola. Let's see how. Now this is the vertex and this is the focus. So because this region, the whole of the region contains the focus, we say this is the interior of the parabola. So this contains focus and hence this is interior region of the parabola. Now the whole of outside of the parabola is called exterior region of the parabola. The difference is interior region contains focus, exterior region does not contain the focus of the parabola, is how we understand the interior region, exterior region. If I want to find a point in the interior region, I identify the region where the focus is existing. If I want to identify the point in the exterior region, I identify the region where the focus does not exist. And of course, the third region is any point on the parabola. So there are two regions, interior and exterior regions for the parabola, connected with focus. So with this, we now define the position of a point where If P lies in the interior region, then I say that this point Px1, y1 is inside the parabola. If P lies somewhere outside in the exterior region, then I say that P is a point outside the parabola. If P lies on the parabola, then this is the third case. So there are three different cases where P lies inside, P lies on the parabola, and P lies outside the parabola. So let's see the three types of positions connected with the parabola. So there are three cases: case 1, case 2, and case 3. Initially, if the point P is outside the parabola, and case 2, where the point is on the parabola, and case 3, where the point is inside the parabola. So in each of the three cases where P is outside, P is on, and P is inside, I have this leading to S11 is greater than 0 if P lies outside, S11 is equal to 0 in case of P lying on the parabola, and S11 is less than 0 for P lying inside the parabola. So these are the three cases which we identified for the parabola y square equal to 4ax, that is S equals y square minus 4ax equals 0. This is how we identify a point inside, a point outside, point on, and point inside. Now let's do some problems to understand the concepts more better. Say for example, I have the question which says, find the focus, vertex, axis, directrix, and endpoints of Latus Rectum for the parabola (3x square minus 9x plus 5y minus 2 equal to 0. So I have a problem here which is given in one of the equation form where I had to find the focus, the vertex, the axis, the directrix, and the endpoints of Latus Rectum for this parabola. So let's see how we can do these kind of problems. Now with the given equation is given to be 3x square minus 9x plus 5y minus 2 equal to 0. Let's try to reduce this into the standard form of parabolas which we have discussed. So in order to reduce this into the standard form, the first and foremost step is to bring all x terms to the left and all y terms to the right, or y to the left and x terms to the right, vice versa. So in this case, I want to bring all x terms to the left because x square is existing in this problem. So taking all x terms to the left and all y terms to the right, this reduces by taking common. I get 3 times of x square minus 3x is minus 5 times y minus 2 by 5. Now in order to bring this in the standard form, I have this in the form of a square minus 2ab that is a square minus 2ab, where I multiply and divide with 2, so that this is in the form of a square minus 2ab plus b squared and minus b squared of this is what we get. Now this, on further simplification, gives 3 times this is a perfect square, which reduces to a square minus 2ab plus b squared, that is a minus b whole square minus 9 by 4 is minus 5 times of this is what we get. So this, on further simplification, gives 3 times of x minus 3 by 2 whole square minus, opening the brackets, 9 3s 27 by 4 is equal to, let's expand with brackets, which is minus 5 y plus 2. 5 get cancelled. Now this, on further simplification, gives 3 times of this whole square is minus 5y plus 2, and minus 27 by 4 on the right is plus 27 by 4, which on further simplification gives minus 5y plus 4 2s are 8. 8 plus 27 is 35 by 4 is what we get. So this, on further simplification, gives minus 5 y minus 7 by 4, which is the transformed equation in standard form, which can be further simplified in standard form. So this equation, when compared with the standard form x square equals minus 4ay, makes us understand that my capital X is x minus 3 by 2 and my capital Y is y minus 7 by 4, and my 4a is 5 by 3. This equals this, that is a equals 5 by 12. So using this, we know that x square equal to minus 4ay has its parabola in the form of inverted, but this is vertex, this is focus, which is given by 0 0 0 minus a, y equal to 0 is how we find each of them, and the axis is x equal to 0. So each of them is obtained through this, so that my focus or my vertex V is nothing but given by x equal to 0 and y equal to 0, which gives me small x is 3 by 2 and y is 7 by 4. And then my focus, which I'm going to have as 0 minus a, will give me the focus of the required parabola. The focus, which is 0 minus a, gives me x coordinate as 0 and my y coordinate is minus a. That implies my capital X, which is nothing but x minus 3 by 2, gives me x minus 3 by 2 equal to 0, and my y coordinate is minus a, that is y minus 7 by 4 is minus a, that is minus 5 over 12 is how we get. So therefore, I get my x as 3 by 2 and my y as 7 by 4 minus 5 by 12, which is nothing but 21 minus 5, which is 16 by 12. and this is 4 over 3. Therefore, the focus S is given by 3 by 2 and 4 by 3 is how we understand the focus of the required parabola is 3 over 2 and 4 over 3. Now, equation of axis is clearly given as x equal to 0. Therefore, for original equation x equal to 0 implies x minus 3 by 2 equal to 0 implies x equal to 3 by 2 is the equation of axis. For the transform equation, this. Next is equation of directrix, as can be clearly seen here, is y minus a equal to 0, that is y, which is y minus 7 by 4 minus a is equal to 0. This, on further simplification, gives the simplification is the LCM of this and this is 12, and 21 plus 5 is 26 by 12 equal to 0, to 6 to 13ths is the equation of the directrix of the parabola in transformed form. Now next comes the endpoints of the lattice rectum, which are L and L dash. As here we can clearly see that the coordinates are 2a comma a comma minus a, and these are 2a comma minus 2a comma minus a. So here clearly I see that this is in the third and the fourth quadrant. So this is 2a and minus a and minus 2a and minus a. So the endpoints of lattice rectum are given by L initially with 2a and minus 2a, 2a and minus a. That implies my x is 2a and my y is minus a, which give me the endpoints. So here my x is x minus 3 by 2 is 2 times of a, that is 10 by 12, and my y, which is minus 7 by 4, is minus a, which is minus 5 over 12. So this is nothing but 3 by 2, 2 5s, 2 6, 5 over 6, 7 by 4 minus 5 over 12. So that is by LCM, x is, it is 9, 14 by 6, and my y is 21 minus 5, which is 16 by 12. 21, 16 by 12, 4 by 3, and 7 by 3. Therefore, my coordinates of L are 7 by 3 and 4 by 3. Similarly, we can find L dash in the similar manner, where I take x as minus 2a and y as minus a, and I get the other end point of the lattice rectum in the similar manner. Now let's see what is a tangent to the parabola. Now we know that a tangent is a line which touches the curve at one or more than one point. The concept of touching gives us three cases which arise from a parabola. Suppose I take the three cases are, I take a parabola and I take the line does not cut the parabola, and in this case the line touches the parabola, and in this case the line cuts the parabola at 2 points, are the three cases through which I get a secant, a tangent, and just a line which does not cut the parabola. So these three cases give us the concept of tangent and its equation and further properties, which we're going to discuss in case of a parabola. The most important is the tangent and its condition and the equation of the tangent with respect to the parabola. Now if I have a parabola, say S, this equal to 0. Suppose there is a tangent which touches the parabola at point P. Now the point of contact is P, and we say that equation of tangent T at P x1 y1 is given by this. We say that equation of tangent at P x1 y1 with respect to the parabola S equal to 0 is S1 equals 0. This is how we identify the equation of tangent at Px1 y1. As we know that S1 is yy1 minus 2a into x plus x1 equal to 0 is how we find the equation of tangent at Px1 y1, and Px1 y1 is called the point of contact. That's how we understand. Now let's see the condition for tangency. That is, if I have a parabola y square equal to 4ax let there be a tangent to the parabola, and let the equation of tangent be y equals mx plus c, where m is not equal to 0 and here a is greater than 0. So if this is a tangent to the parabola, then the condition for tangency is the condition for the line y is equal to mx plus c to be a tangent to the parabola y square equal to 4ax is that c must be equal to am, or you can also take this as a must be equal to c times of m, the product of slope and y-intercept. Is how we understand the condition for tangency. Now let's see the limitations of the tangent. As we have seen clearly here, I have taken the tangent with restrictions that slope is not equal to 0. What? The question comes here, what if m is equal to 0? So what happens when the slope is 0? Why can't I accept m equal to 0 for this line to be a tangent to the parabola in case of condition for tangency? So let's see. M equal to 0, that is the slope m equal to 0 implies the line is parallel to x-axis, because any line parallel to x-axis has its slope 0 and slope of x-axis itself is 0, implies the line y equal to mx plus c is parallel to x-axis. But as the parabola extends to infinity, you cannot have a line which is parallel to x-axis and acting as a tangent, because as this parabola extends up or down, it opens up and then the line does not touch the parabola. That implies the line meets or touches the parabola at infinity, is how we understand. Now, because the line touches the parabola at infinity, that implies tangent does not exist for m equal to 0. Therefore, in order that a tangent exists for the parabola, the condition is m is not equal to 0, as how I understand the condition of tangency restricted with the condition m not equal to 0. That is, the slope of the line is non-zero. Now, let's connect the condition for tangency with equation of tangent. Now, we know that the condition for tangency is c equals a by m, and therefore, when I say y equal to mx plus c is the tangent, c can be replaced with a by m. Therefore, y equal to mx plus a by m is said to be the tangent of the parabola. So, if we know the slope and the value of a, we can construct the tangent for the given parabola. So, this is the condition for tangency reduced to the equation of tangent, which is mx plus a by m, and the point of contact here is given by p, that is am square and 2a by m, is how we define the point of contact. Or this is also given by, in terms of c, it's given by c by m and 2c. If the value of c is given, we reduce using the condition c equals a by m, is how we understand the point condition, the equation of tangent, and the point of contact of the tangent with the parabola, this, and this. Now, let's study the properties of tangent with respect to x and y axis. So, tangents with respect to x axis and y axis. Say, for example, I take the parabola y square equal to 4ax, and then I see that there is only one tangent which can be drawn parallel to y axis or y axis itself. Therefore, if I take x axis, there is no tangent which is parallel to x axis, as we have seen in the previous case. No tangent parallel to x axis. But when I take the y axis, I see that there is only one tangent parallel to y axis. Only one tangent exists which is parallel to y axis or y axis itself, is how we understand the tangent connected with the parabola. Now, let's see the concept of tangents from an external point. So as we know that there are three positions of points, one is inside the parabola, on the parabola and outside the parabola. So we have three cases which arise with the tangents. So as I take here a parabola and I take a point P inside, and I take a parabola and a point P on, and I take a parabola outside, then I say that in this case of P lying inside the parabola, no tangents can be drawn. For a point P on the parabola, there is only one tangent which can be drawn on the parabola. For a point P outside, there are two tangents which can be drawn from a point outside the parabola. Therefore, from an external point, there are two tangents which can be drawn. So in case of P on, one tangent, and in case of this, two tangents and no tangents. No tangents if P is inside, one tangent if P is on the parabola, and two tangents if P is outside the parabola. That's how we understand the concept of inside, on and outside. Next, let's see the equation of chord joining 2 points. So for example, I have a parabola y square equals 4ax. Now here, if suppose I have a chord which cuts, a secant which cuts the parabola in 2 points, that is A and B, where here AB is called the chord of the parabola. Now the chord AB can be found with its equation using the formula with S equals y square minus 4x equal to 0, implies equation of chord AB is given by S1 plus S2 equals S12. Is how we understand the equations of chord, where this is given by the coordinates x1, y1, and this with x2, y2. So equation of chord joining ax1, y1 and bx2, y2 is given by S1 plus S2 equals S12. Normal to the curve. So what is a normal to the parabola? As we have discussed, the normal concept in a circle is a line which is perpendicular to the tangent and passing through the point, is the similar definition which we give for a parabola. So let's see the normal for a parabola. Say for example, I have a parabola y square equals 4ax, with this being x-axis and this being y-axis. If suppose I take a tangent to this parabola is given by this at the point P x1 y1, then a line which passes through P and perpendicular to T is called the normal. That is, a line which passes through P and is perpendicular is called the normal. A normal is a line perpendicular to tangent. So N is perpendicular to T and passes through P x1 y1. So this is called the normal and this is called tangent. So normal and the tangent. Equation of normal. Let's see the equation of normal for the concept of normal. I have now in the previous case I have defined the tangent and perpendicular to this as the normal. Now in order to find the equation of normal, I need to find equation of this line, which is given by equation of normal at p x1 y1 is given by y minus y1 equals as this. So equation of normal is y minus y1 equals minus y1 by 2a into x minus x1. This is how we identify the normal. And similarly, we have slope of normal, which is given by minus y1 by 2a. So slope of normal is minus y1 by 2a, and equation of normal is this equals this. Is how we understand the tangent and normal with their respective equations. For the parabola in standard form, y squared equal to 4ax. Now let's see the equation of tangent in parametric form. So now that we have discussed about the parametric equation of a parabola, let's see what would be the equation of tangent in parametric form. So let's recap with the parametric representation of a parabola y squared equal to 4ax. Suppose I take the parabola y squared equal to 4ax. And let P be a point represented by the parametric point T. Now here the parametric point T is referred with AT squared and 2AT. So the parametric point T indicates the coordinates are AT squared and 2AT, as we all know, which satisfies the parabola y squared equals 4ax. So with this parametric point, let's see what is the equation of tangent at this parametric point. If this is the tangent to the parabola, then the equation of tangent in parametric form is given by x minus yt plus at square equal to 0, where t belongs to real numbers. Is how we define the equation of tangent at the parametric point t. So equation of tangent at t is given as x minus yt plus at squared for the parabola y squared minus 4ax equal to 0. Is how we understand the equation of tangent in parametric form. In similar manner, if I want to find the equation of normal, let's draw the normal for this parabola y squared equal to 4ax. So if I have a normal passing through P, which is perpendicular to the tangent, then equation of the normal at the point P is given by the formula equation of normal at P of t, that is passing through P of t and perpendicular to the tangent, is given by y plus xt equals 2at plus a t cube, where t belongs to real numbers. So equation of normal at p of t is n, that is y plus xt is equal to 2at plus at cube, where the parametric point t is at square 2at. T is a real number. Now let's see the concept of number of normals through a given point. So what does this mean? If I take a point in the plane where a parabola exists, then there are totally 3 normals which can be drawn to the parabola from that point. So let's see how we can mathematically support that exactly there are 3 normals at the most which can be drawn from a point to the parabola. Suppose I have a parabola y square equals 4ax. And P is a point out here. Now let me say there's a normal which passes through PE out here. Now we know that the equation of the normal is n is y plus xt is 2at plus at cube. Now let me take a point px1 y1 on the normal. That is, let's say the normal passes through the point x1 y1. If the normal passes through this point a x1 y1, that implies a x1 y1 belongs to the normal, which is equation 1. So if this point lies on 1, that implies it satisfies the equation y1 plus x1t is 2at plus at cube, which on further simplification gives at cube plus 2a minus x1 of t minus y1 equals 0. So this is a cubic equation in T, which is cubic equation in T. Now since this is cubic equation in T, it has 3 roots for T, that is 3 parametric points. That implies there exists 3 roots for this. That implies there exists 3 roots in the sense there exists at the most 3 points, that is all the t's, which are t1, t2 and t3. There exist 3 points. One is t1, one is t2 and one is t3 at the most, which shows that there are normals on the parabola at 3 points t1, t2 and t3. That is, there exists at the most 3 normals from ax1 to the parabola y square equals 4ax. So at the most there are 3 normals from here ax1 y1 to this, one of the normal being n1 and the other normal being being n2, that is p of q of t2, and the third normal would be somewhere else. T3, and then this would be the other normal which passes through R T of 3. So there are three normals which passes through A. One is normal 1, and the other is normal 2, and the other is the third normal which is out here. So N1, N2 and N3 are the three normals which at the most exist for the parabola. So there can be one normal, two normals, or three normals from a point to the parabola y square equal to 4ax, because this is a cubic equation in T. Now let's see the number of normals as a criterion or the condition. So coming with the equation of normal, we know that equation of normal is y plus xt is equal to 2at plus at cube. And if p x1 y1 or ax1 y1 in the previous case lies on the normal, then we have the condition x1 at cube plus 2a minus x1 of t minus y1 equals 0 is what we get if you substitute the point in the normal. Now this being a cubic equation, we get this with let h equals 2a minus x1 by 3a and g be equal to minus y1 by a is how we take the case. Now with these two values of h and g, we define the number of normals. So with this, we have three cases of with delta, which I define as g squared plus 4h cube. I get three cases to which I define the number of normals as 1, number of normals as 2, or number of normals as 3. So now that I have h equals 2a minus x1 by 3a and g equals minus y1 by a, my delta is given by the formula g squared plus 4h cube, the proof of which is beyond the syllabus on assuming delta. So using delta equal to this, I have if delta is greater than 0, the second case being delta equal to 0 or delta is less than 0. So in this case, number of normals will be 1. So if delta is greater than 0, I get the number of normals to be 1. And if delta is equal to 0, then I get number of normals is 2. And then if my delta is less than 0, I get number of normals is 3. Is how I understand the cases as case 1, case 2 and case 3. Delta greater than 0, there are only one normal. Delta equal to 0, there are two normals passing through ax and y1. Delta is less than 0, then there are three normals passing through x1, y1 to the parabola y squared equal to 4ax. Is how we understand the three cases. And here, assuming that x1 is not equal to 2a and y1 is not equal to 0, is how we assume in these two cases. And however, it is important to note that x1 equal to 2a and y1 equal to 0 implies number of normals is an exceptional case is equal to 1, is how we understand the note. So if x1 is equal to 2a and y1 equal to 0, then also the number of normals is 1 as a special case. Criterion for number of normals connected with the delta equal to 0, greater than 0 and less than 0. Now let's see how we can find the point of contact of the tangent. So the topic is about finding the point of contact. With the tangent. That's how we understand the concept. So finding the point of contact, say for example, I have an example problem which says show that 7x plus 6y equal to 13 is a tangent to the parabola y square minus 7x minus 8y plus 14 equal to 0, and hence and find its point of contact. This is how the question reads. So in this case, clearly the parabola given is y square minus 7x minus 8y plus 14 equal to 0, which on further simplification gives us let me take this as equation 1. Now we have the condition that the line Lx plus my plus n is a tangent to the parabola y square equal to 4ax if n square a is equal to ln. So let's initially take this in the standard form. Therefore, equals 7x is what I get, which on further simplification gives me y square 2 times of 4y, that is 8y. Now this being 4, I add and subtract 4 square plus 14 equals 7x is what we get. So reducing this in the standard form, I get this as y minus 4 whole square equals 7x minus 16 plus 14 is minus 2, which comes as plus 2 on the right, is what we get. So therefore, this when reduced to the standard form gives y square equals 7 times of this. So as I see here, my 4a is 7, which gives me a equals 7 by 4. And when I have the line 7x plus 6y minus 13 equal to 0, I have this in the form Lx plus my plus n equal to 0, where this is L, this is m, and this is n. So using these 4 basic values, I have the condition for tangency. Now condition for tangency is given by m square a equals nl. This is the formula which we have discussed as the condition for tangency. Therefore, using this, if the left hand side is m square of a, that is 7 by 4, which gives me 36 79663, and my right hand side, which is NL, gives me N times as minus 13 times L, which is 7, which gives me minus 91. Now, as we can clearly see that my m square a is not equal to NL, therefore 2 is not a tangent to the parabola given by equation 1, is how we conclude, and therefore there exists no point of contact. This is how we conclude the point of contact connected with the tangent. So this condition doesn't satisfy, therefore this line is not a tangent to the parabola, and hence there is no point of contact. The condition for tangency. Now, what's the condition for tangency in parametric form is what we're going to discuss here. Suppose I have a parabola y square equals 4ax, and say I have a line which touches the tangent at P of t, and the equation of this line is given by Lx plus My plus n. So I want to see the condition for this line to be a tangent to the parabola y square equal to 4ax. Now clearly we know that equation of tangent at P is given by x minus yt plus at square equal to 0 in the parametric form. We have already discussed this as the formula. Now the equation of tangent is already given to be Lx plus My plus n equal to 0. Now since the parametric form of tangent is this and the equation of tangent given is this, both represent the same tangent. Therefore 1 and 2 represent the same line. Therefore their corresponding coefficients must be in same ratio, that is L by 1 or 1 by L equals minus t by m, and that equals at squared by n is what we get. So from these two I get t equals minus m by L, and from the first and last equation I get at squared is n by L, that implies a times of t squared, which is minus m by L whole square, is n by L, because this is simply substituted with t equal to minus m by L in place of t squared. That gives us am squared is nl. Is how I get the two conditions given by am squared equals nl. This is condition for tangency. So condition for tangency that the line Lx plus My plus n equal to 0 is a tangent to the parabola y square equal to 4ax is simply am square must be equal to n times L. Now finding the point of contact, that is the point T, in terms of L, M, N and A. So let's see how we can find the point of contact. Now the point of contact here is P of T is already given as AT square and 2AT in the parametric form. But in the previous case, we have discussed that T is minus m by L, which we have obtained through the proportion of these two, where L by 1 or 1 by L equals minus T by m. So T is minus m by L, which I get from these two equations. So using the value of T as minus m by L, I just simplify, substituting in the point. So with T equals minus m by L, substituting this in this, we get P of T is AT square, that is A times T square, and 2A T is what we get. So in place of T, which is substituted here, I get this to be am square by L square and minus 2am by L is what we get. As the point of contact. So my point of contact of the line Lx plus my plus n to the parabola y squared equal to 4ax is am square by L square and minus 2am by L, or this can also simplified to be n by L and minus 2am by L. Both are these points of contacts in their different forms for the parabola y square equal to 4ax with the line Lx plus my plus n equal to 0. The point of contact of the line with the parabola.